We've looked at language modeling, and we did it with the GRU. We looked at neural style transfer, and in previous videos we looked at variational auto-encoders. And let me just remind you what we're trying to do. We have a bunch of data. This can be text, this can be images, this can be music. Yeah? And this data has a certain distribution, P of X, that we don't know. Alright? And what we try to do is to regenerate the image from the beginning. Yeah? So we basically gonna transform this data into a latent space, usually lower dimensions than this one, right? And then we're gonna transform the data back to, with the goal of getting exactly what we put in. All right? And then, so it's all about this C here. We want to construct a generator. That means that we don't really want to reconstruct the input. We basically want to find X of G, G of generator. Yeah, so generator. And the goal of the generator is to generate samples that come from this distribution. Yeah. So X generate should come from the distribution P of X. Now again, we don't know P of X. So what we can do is we can actually choose P of Z, and mostly we'll choose a Gaussian. Yeah. And this is what we did exactly in variational auto-encoders. So we defined the probability Z here, the probability distribution from Z, we assumed it to be a Gaussian. And if you assume this to be a Gaussian, yeah, you can actually maximize the likelihood of seeing the data. But we saw that we cannot optimize P of X directly. Yeah, this is an integral over a lot over Z's, over the whole spectrum of Z's, and it's intractable. So you cannot calculate that integral. So what we do instead is we're gonna maximize a lower bound of P of X. And this lower bound we have called L. Alright, so this is what happened in variational auto-encoders. Now let's go to GANs, and GANs is the topic of this video. GANs are Generative Adversarial Networks. It dates from 2014 and was introduced by Ian Goodfellow et al. So the whole point here is that we're gonna give up in guessing what this distribution of Z will be. Yeah. So we're not gonna explicitly model P of X by P of Z. Yeah. So what we're gonna do is we're gonna sample from P of X and learn P of X. Yeah. So to set that up, we're gonna play a two-player adversarial game. So you have two players, and one player is called the generator, generates data, and the other player is called the discriminator, and the discriminator examines the data and decides if the image is real or fake. So we're talking about images here. So here in the drawing, we have our data. It's the same as this one here. It's our data X, or images X, distributed according to P of X that we don't know. So this is our training data. And what we have here is we have a generator, and the generator takes an input from Z. Let's call this input Z, and Z is just random noise. We're not gonna say Z needs to be Gaussian or whatever, no. Z in this case is just random noise. And the generator takes in the random noise, yeah, and then the output is fed into the discriminator. Alright? So the output is fed into the discriminator, and then the discriminator calculates the probability that the image is coming from here or from here. Yeah, so the output is a probability that the image comes from here, and the probability that the image comes from here. Alright? Now, what is the end game? Well, the end game is that the end game of the generator is to fool the discriminator. And fooling the discriminator basically means that these two probabilities are 50%. So that the discriminator is not able to choose between one or the other. So that is the end game for G. And generator and discriminator are both neural nets. Yeah, these are complex functions. The generator neural net is parameterized by phi, whereas the discriminator is parameterized by theta. And so whenever we call a loss here, the loss that we calculate is backpropagated back to G and D, and the thetas and the phis are updated with every iteration.